In this video, we're going to be looking at the concept of mass, specifically the types of mass that deal with internal and gravitational properties. What are we going to do? In this presentation, we are going to define mass. We're going to look at the function or functions of mass. We're also going to understand how mass relates to Newton's laws of motion. We're going to start looking at how Newton's three laws of motion all relate to one another. And we're also going to define the different types of masses, because there is more than one type of mass. And we're going, or at least to say there's more than one type of definition for mass, and we're going to compare them. Why are we doing this? Because understanding mass is vital to understanding how objects react when there's an external force that's trying to create a change upon them. Mass is defined and viewed very differently in physics than it would be in chemistry or biology. I'm not going to say physics perspective is better. I'm not going to say it's more correct. I'm going to say that it's different and it's more applicable to what we do. From a chemistry point of view and a biology point of view, their definitions are more applicable for them, so it probably suits them better than what a physicist would view. For you, it's important that you understand all these different types of perspectives of mass, because you never know what you're going to be facing. So we've already talked in earlier presentations and through our classes the Newton's second and third law of motion, where Newton's second law of motion is that the net external force, that's the forces that are generated outside of our system or object, where the net external force acting on an object or system equals the mass of that object or the system multiplied by that object or system's acceleration. It's often written as a straight-up equation where we see the summation of forces equals mass times acceleration. And these are actually going to be vector values that we'll be talking about later on. But for right now, we'll just turn around and say it's the net force, the total of all forces added up, equals mass times acceleration. Newton's third law is that classic action-reaction situation where it really says that whenever one object pushes on a different object, so whenever object A pushes on object B reacts by pushing back on A just as hard, but in the exact opposite direction. So third law is always dealing with internal forces of a system, because it takes two objects or two things, two systems interacting on each other. So the third law, again, is all about internal forces. Second law is all about external forces. And the big question is, why do these forces work? I mean, why do these laws work? Why do they exist? And why are they the second and third law? And what about the first law? And the reason for that is because these two laws work because of the first law. The first law is often the foundation law that sets the stage for every law that follows after it. Newton's first law is often known as the law of inertia, something that you might have heard in earlier classes, hopefully that you have. And sometimes it is taught simply by people saying inertia is an object in motion, stay in motion, while objects at rest stay at rest. And if that was the case for you, do yourself a very important favor. Forget that. It is totally wrong. It is not right. It is so off base. And the reason for that is it has been oversimplified. Newton never said this way. He had said something that was more involved. This is now being taken out of context to the point on where this has a totally different meaning, and it's totally incorrect. Okay? Sometimes people often have a slightly more involved statement. They'll say, well, an object in motion tends to stay in motion, while objects at rest tend to stay at rest, unless acted on by an outside force. And that sounds more accurate, but is still completely wrong, because it's still way too oversimplified. For example, If I have a box that's resting on the floor and I'm pulling to the right with a force of 50 newtons and someone else is pulling to the left with 50 newtons and the box has a weight of gravity that's 80 newtons going down, but the floor is holding it upwards with a force of 80 newtons, that box is at rest. And it will remain at rest. But there are outside forces acting on it. Likewise, we have the moon orbiting the Earth. Why does the moon orbit the Earth? We all know there's a force of gravity pulling down on the moon towards the Earth, but the moon is in motion. And if objects in motion stay in motion, unless acted on by an outside force, then this force of gravity should stop the moon and we should die. But we don't, and I'm very happy that that's the case. I'm very happy that the moon is not going to kill us. But what we have here as our law is incorrect. And the reason is, again, it's oversimplified. It's been taken out of context, changing the true meaning of this law. And in elementary school and in middle school, we're not going to be asked anything that's overly complicated. Your teachers are often kind of okay with that. You know what? You'll learn it more later on. They'll get more in depth with it. And now you're at later on, and we start to go into this, and you'll go, I know this. I learned it back in elementary school. I did a worksheet on this. And the next thing you know, when you get asked those real in-depth questions, you have no idea what to do. And that's because you have been disarmed, because you need to have a deep understanding. And to have a deep understanding of a law, you need to know what the actual law is. It's not complicated. It's just been abbreviated way too much. Newton's first law really says the following, that the speed and direction that an object has, or a system, whatever speed and direction it has when it is moving, does not change unless there is a net unbalanced external force acting on the object or system. There's the thing on that. When I take a look at this box over here, I have external forces, but they net out to zero. They balance. There is no unbalanced force here. So there's no reason for the motion to change. But the moment this 50 becomes 90, yes, this box will no longer stay at rest. Please notice, the moon is moving, but it's changing direction. There's an unbalanced force, and it's changing the direction of the moon's motion. So this makes perfect sense. And so Newton's first law, again, really is just that the speed and direction that an object has in its motion, or a system has in its motion, does not change. A system's or an object's motion does not change in any way unless there is an unbalanced force acting on you. And no motion is a motion. So if I'm not moving, I'm going to still not move unless there's a net unbalanced force to change that. Inertia has always been defined as an object's resistance or a system's resistance to change in motion at either speed and or the direction. That's what inertia is, and that's why we call it the law of inertia, because it's about resisting change in either speed or direction being caused by an unbalanced net external force. So that's our foundational law, and it now stems to the other two. Because if we look at Newton's second law, net force equals ma, and mass is going to be dealing with inertia, my resistance to change, then yes, this makes perfect sense, because my acceleration will be inversely proportional to my mass. So the more inertia I have, the smaller the acceleration is going to be. But how does an object resist a force? When I am just standing off to the side of the road and someone tries to get me to go somewhere else, how do I resist when they push me? That's where the third law comes in. I push back. I'm going to push back just as hard as you're pushing on me for just as long, and I will stop the moment you stop because I don't want to change what I'm doing. The third law is a consequence of the first law because I don't want to change what I'm doing, and when you try to make me change, I'm going to try and change you back. The second law deals with how I'm actually going to be affected by you influencing me. Both come from that first law. So now how do we define mass? After all, if net force equals mass times acceleration, how do we define mass? And this comes down to its application. If mass is going to be my net force over acceleration, we can say mass is how well an object resists a change in its motion caused by a net external force. We call this mass inertial mass. Kind of makes sense if you think about it, because resisting a change in motion caused by an external force is inertia. So when I'm using inertia to find an object's mass, I'm finding what is called inertial mass. So we see this all the time. In chemistry, we often tell you it's how much matter makes up a material, how many things there might be, and that works to a point, but please notice that even in chemistry, every time you work with mass, it was about resisting change. So here's an equation or a concept dealing with the specific heat of a material, how much heat is needed to cause a temperature change. I'm sure it's bringing back lots of warm, fuzzy, wonderful memories for you guys. And if we just take a look at this, we can say that Q is the amount of heat that's being pumped in. That's going to be a lot like our force. Delta T is our temperature change. And this here is our mass. Now, we don't have to worry about specific heat right now because I'm just looking at the relationship, but please notice that the change in temperature, like acceleration, how things change, is inversely proportional to the mass. The more mass I have, the harder it is to change the temperature. That's why if you want to make a nice hot cup of coffee and you just want a cup, it's not a good idea to fill up an entire coffee pot because you're going to have to wait a long time to heat up all that water. Just give enough water to heat up, just enough water to fill a coffee pot, a coffee cup, and you'll be fine. You'll get done a lot faster. So mass has always been about resistance. We see this historically as well. A country or a government tries to create a change on a population. The population will always resist because this isn't how we've been doing things. We don't want this. We didn't ask for this change. And the very large populations have a much easier time resisting than small populations. And that's just because there's more people there. There's more social mass. This mass is all about resistance to change. Okay. Now, if you're thinking, well, what about large groups of people that are trying to create changes? Sure, but let's be honest. If I'm in a group that's trying to create a change, then that's what we're doing. So when you try to stop me from creating a change, you're stopping me from what I am personally trying to do. And so I'm going to resist that change on what my present motion is. Remember, Newton's first law is not that I'm going to start to move or not move, but I'm going to change whatever it is I am doing. And so the same thing applies to societies. All right. We also see that there's a relationship between mass and gravity. For example, we know that the more mass you have, the heavier you weigh. Back in chemistry, for example, when you had to find the mass of an object, odds are you didn't exert a force on it as you threw the beaker across the room, but someone had a stopwatch to try and measure the acceleration. In fact, if you're taking a chemistry class right now and you're in a chemistry lab, do not take beakers and throw them across the room to try and find out what their mass is. You will run into very serious trouble. So that is not something that I encourage you to do. What you do instead is you place it on a scale and you measure the mass that way. And the scale is geared and calibrated to correlate the gravitational force to the mass of the object. And we know that if you go to the moon or some other place like that, the scale will give you the wrong mass because it's not measuring mass, it's actually measuring gravitational force. When I'm using the force of gravity, such as by way of a scale to find the mass of an object, I'm finding what's called gravitational mass. So we often define mass or give mass a name based on how we're going to find it. If I'm finding an object's mass by way of net force and acceleration, I'm finding inertial mass because I'm going to see how well that mass resists the influence of a force or an external force. If I am dealing with how this relates to the force of gravity, I'm dealing with gravitational mass. This has a wonderful convenience that I don't need a lot of space. It's very easy to do. However, gravitational mass measurements are highly restricted to geography. If I have a very sensitive mass scale and I go ahead and use it here at sea level, and then I try and use the same scale up at Mount Everest, I'm going to come up with different readings of mass for the same object because the gravitational forces are different. And if I am going off in orbit or I'm leaving the Earth and I'm going somewhere else, that scale is going to be a wonderful paperweight, assuming there's enough gravity for it to actually act as a paperweight, because it is going to be out of calibration. I will not be able to use it for any accurate measurements. The good news, though, is mass. So inertial mass, gravitational mass, they are exactly numerically equal. It all comes down to how are you finding it. So we're not debating here which mass is the better mass. It's just how are you finding this. And we're not going to argue with chemistry people or biology people when they talk about the quantity of matter that makes up this material, because in the end, that's equal to what we have as well. So it comes down to what is your application of mass, or for the mass. So again, chemistry and physics, we are going to totally disagree on what mass is, and to argue over who is right is a stupid argument, because we are both right, because we're using this in a based upon how we're going to be using it. Physics will always be based upon resistance to change, resistance to gravity, resistance to any type of force. Chemistry is all going to be about the amount of matter that makes an object up. And I'm not going to lie, if I have an ice cube and an iceberg, the ice cube is going to have way less molecules in it, way less matter than the iceberg, even though they are chemically identical. But if I want to accelerate an ice cube from rest and throw it across the room, I can do it fairly easily. I've done it before for a myriad of reasons. But for me to try and get an iceberg to accelerate, no, sorry, can't do that. There's just way too much mass. Likewise, if I want to measure the force on a scale, the ice cube is really easy to do. I cannot find a scale strong enough to hold up an iceberg. So these two opposing points of view really are still supporting the same thing. It just comes down to which application are you looking at. All right, so that's going to wrap up our presentation on mass. It's going to be working very much the same way as always. It's going to be just something that we measure, but you need to understand when I'm asking for inertial mass, you have to be able to use the law. If I'm looking for gravitational mass, you'll have to be able to use the force of gravity for that. And realize in the end, no matter what type of mass you're finding, you're going to find the same quantity because all masses are the same. Mass is mass, no matter how you see it, no matter how you view it. All right, if you have any questions on this, do not hesitate to let me know. We will be discussing this and applying this much more in class. So thank you for watching the video.